Backpropagation is the algorithm that teaches a neural network how to change its inner settings so its guesses get better. In this video, we will explain the key concepts you need to understand backpropagation, show the math and the chain rule so you can see how gradients are computed, walk through a concrete numeric example step by step, and finish with an easy to remember analogy. Before we dive into backpropagation itself, you need to understand a few things. First, what a neural network does in a forward pass. A neural network is a layered function that converts inputs into outputs. Each neuron computes a weighted sum of its inputs, adds a bias, passes the result through an activation function, and passes that forward. We call the collection of weights and biases the network parameters. Next, loss function. To train the network, we need a way to measure how wrong its input is. The loss function gives a number that tells us how bad the prediction is for a given example. A common choice is mean squared error for regression or binary cross entropy for probabilities. The loss is what we want to minimize. We will also need to know about gradient and derivative. The gradient is the derivative of the loss with respect to a parameter. It tells us how the loss would change if we tweak the parameter a tiny bit. Backpropagation is the process of computing those gradients efficiently for every parameter in the network, using the chain rule from calculus. Finally, the learning rate and update rule. Once we have the gradient, we update each parameter by moving it a little in the opposite direction of the gradient. Opposite because we want to reduce loss. The learning rate is a small positive number that scales how big that step is. Update rule in brief. New parameter is equal to the old parameter minus the learning rate multiplied by the gradient. Backpropagation computes the gradient of the loss with respect to every weight and bias in the network. It does this by propagating error information backward from the output layer to the earlier layers using the chain rule. So conceptually, first, do a forward pass to compute outputs and loss. Second, compute how the loss changes with respect to the outputs. Third, propagate that change backward through the activation functions and weighted sums to find out how the loss depends on each parameter. Finally, use the gradients to update weights. Backpropagation reuses intermediate derivatives computed for later layers so we do not recalculate the same pieces multiple times. That is why it is so efficient. Now, let's walk step by step through an example. We will use a tiny network so you can follow every number. Our network architecture consists of two input nodes, x1 and x2, one hidden layer with two neurons, h1 and h2, each using the sigmoid activation, one output neuron, O1, sigmoid activation as well. Loss can be represented by 0.5 times y minus O1 squared. Our initial values will be small numbers so that the math is manageable. Inputs. x1 is equal to 0.05, x2 is equal to 0.1. Our target is y is equal to 0.01, meaning we would like our model to take our inputs, x1 and x2, and eventually learn to output our target. Our hidden layer weights and biases are, for h1, our weight from x1 to h1 will be 0.15, our weight from x2 to h1 will be 0.2, and our bias for h1 will be 0.35. For h2, our first weight will be 0.25, our second weight will be 0.3, and our bias will be 0.35 as well. From h1 to our output layer, our weight is 0.4. From h2 to our output layer, our weight is 0.45, and the bias is 0.6. The activation function is the sigmoid function. The learning rate is 0.5. Step 1. Forward pass. To compute our first hidden neuron, we first have to multiply our first input by its respective weight plus our second input times its respective weight, and we add the bias to it. This results in 0.3775. We then apply our sigmoid function to it, which gives us approximately 0.59. To compute our second hidden neuron, we do the same. First input multiplied by its respective weight plus our second input multiplied by its respective weight, and we add the bias to it. We get an approximation of 0.39. We apply the sigmoid function again and approximately get 0.596. Now we do the same computation for our output neuron, but this time we use our hidden neurons' outputs as our new inputs, as well as our hidden neurons' respective weights as our new weights. After our computation, we get 1.1. We apply the sigmoid function and get approximately 0.75. Now we compute the loss using mean square error and approximately get 0.27. We now know our error. Now we need to fix it. This brings us to step 2, the backward pass. We need to calculate the gradient. Think of the gradient as the blame game. We need to figure out exactly how much specific weights, like this one here, weight 3,1, contributed to that error so we can adjust them. Step 2, the output layer gradient. To find this, we use the chain rule. We can't calculate the gradient in one big step, so we break it down into 3 manageable parts. First, the mistake. How far was our guess? 2, the sensitivity. Is the neuron currently capable of learning? 3, the input. How strong was the signal coming in? Let's calculate them one by one. First, the mistake. We compare our prediction, 0.1, to the target. Our prediction was roughly 0.75. The target was 0.01. So our raw mistake is roughly 0.74. We guessed way too high. Next, the sensitivity. This comes from our activation function, the sigmoid. We multiply the output by 1 minus the output. This gives us a slope of roughly 0.18. Now we combine the mistake and the sensitivity to get the error signal, which we call delta 3. This represents the pure error sitting at the output neuron. Multiplying 0.74 by 0.18 gives us a delta 3 of roughly 0.138. Keep this number in mind. We will use it for everything else. Finally, we calculate the gradient for weight 3,1. We take our error signal, delta 3, and multiply it by the input that traveled through that wire, H1. Why multiply by the input? Because if the input from the previous neuron was 0, this weight wouldn't have mattered. But here the input H1 was strong. So 0.138 times 0.59 gives us our final gradient 0.082. We do the exact same thing for the second weight, W32, using its specific input, H2. That gives us 0.0826. And for the bias, the input for the bias is always 1. So the gradient is just the error signal itself, 0.138. Step 3, backpropagating to the hidden layer. Now we go deeper. We've calculated the error at the output, but the output neuron didn't act alone. It got instructions from the hidden layer. We need to figure out how much of the error is the fault of hidden neuron 1, H1, and hidden neuron 2, H2. Let's look at H1. To find its error signal, we need to pull the error backwards across the bridge. We take the output error, 0.138, pull it back across the weight, 0.4, and multiply by the slope of H1 itself, 0.241. This gives us 0.013. This is the blame assigned specifically to hidden neuron 1. We do the same for H2. We take the output error, pull it back across its weight, 0.45, and multiply by its slope. This gives us 0.014. Now that we know the error for the hidden neurons, calculating the gradients for the very first layer of weights is easy. To find the gradient for weight 1,1, we take the error of the hidden neuron, 0.013, and multiply it by the input x1, which is 0.05. The result is a tiny number, 0.0006. We repeat this for the other weights, and just like that, we have successfully calculated the gradients for every single weight in the network. Now for the payoff. We have the gradients, we know exactly which direction increases the error. So to decrease the error, we simply move in the opposite direction. We take our old weight and subtract the gradient, but we don't subtract the full amount. We scale it down using our learning rate, which is 0.5. Let's update weight 3,1. It started at 0.4. The gradient was 0.082. So we calculate 0.4 minus half of 0.082. That gives us a new weight of roughly 0.359. Notice the weight went down. That makes sense. Our prediction was too high, so we are lowering the connection strength to fix it. We do the same for the others. Weight 3,2 drops to 0.408. The bias B3 drops to 0.531. Back in the first layer, the weights change by tiny amounts because they are deeper in the network. So did it work? If we ran a forward pass again with these new weights, our prediction wouldn't be 0.75 anymore. It would be slightly lower, closer to our target of 0.01. And our loss, the error, would be smaller. But we aren't done yet. One step doesn't get you at the bottom of a mountain. To fully train the network, we repeat this loop. Forward pass, back propagation, update weights thousands of times. Step by step, the error drops and the model learns. Let's give you an analogy that will help you understand this better. Imagine a kid trying to throw a ball into a basket. The kid throws the ball, watches where it lands, and adjusts the next throw. So first, we have the forward pass. The kid throws the ball. That is the network making a prediction. Second, we have the loss, aka the error. The ball misses, the farther it misses, the bigger the error. 3. Back propagation. Now the kid asks, was I too far left, too far right, too short, too strong? They figure out how each part of the throw contributed to the miss. That's exactly what backprop does. It figures out how much each weight contributed to the error. 4. Gradient descent. The kid adjusts their next throw based on the feedback provided by backpropagation. Not too much, not too little, exactly like tuning the weights by a small step. Step 5. Repeat. Throw, get feedback, adjust over and over until the throw hits the target. This is backpropagation. Make a guess, see how wrong it was, and adjust the parts that caused the mistake. So let's do a quick recap. Backpropagation computes derivatives of the loss with respect to every parameter using the chain rule. It does a forward pass to compute outputs, then a backward pass to compute gradients. We update parameters by stepping opposite to the gradient scaled by the learning rate. Repeat this across many examples and the model improves. If this made backpropagation click, please like the video, subscribe for more clear AI explanations, and comment with what topic you want explained next. And as always, thank you for watching, and I'll see you in the next one.